the first invited speaker of the day, Dr. Somayeh Khakpash. Somayeh is a graduate of LEI, and she has been a postdoc with me at the University of Delaware for 2 years. But now she's moving on to go to Rutgers with the LSST Catalyst Fellowship, which is a new name fellowship that was set up by the LSST Corporation and sponsored by the Templeton Foundation. And Somayeh will talk about microlensing science with Rubin. I'll give you a 5 minutes warning.
Okay, thank you. Hi everyone. I'm so happy to be here today and so excited to be at an in-person workshop finally. And I would love to thank the organizers for inviting me to give this talk. I've really enjoyed how you've put together all these different topics, and I've really enjoyed it so far. And so before I give my talk, just wanted to give you some background of like what I've been working. So for my dissertation, I've been working on like exoplanetary microlensing, but on the like data science aspect of that. And I moved on to my postdoc position working on light curves with supernova, again, the data science aspect of that. And the next position will be on quasar microlensing, again, data science aspects. So this is like the whole theme and the projects I've been working on. Today, I want to talk about microlensing science with Rubin. Since the beginning of this week, we've heard a lot about strong lensing and microlensing actually of the extragalactic sources. But today I want to talk about microlensing of like stellar stars, planets, and compact objects. So like a different aspect of microlensing. In this talk, I will first introduce microlensing, and basically my goal is to show you what aspect of microlensing we're exactly talking about. And I will then mention like why we're talking about Rubin and microlensing, and then I will talk about the TVS microlensing subgroup, and some of the activities we've been doing within that subgroup. And then at the end, I will talk about part of the work that I did as my dissertation and how I've been like redirecting that towards Rubin's goals. All right, so the image on the left, you've seen it a few times this week. Gravitational lensing happens when a light coming from a distant source is bent by another object along the way. And then as a result, the image of the distant source is formed on a ring around the lens object. The ring is the Einstein ring, and the radius of that is proportional to the mass of the lens. And in this case of this image, strong lensing, the lens is so massive enough that you can actually resolve the image. But in the case of microlensing, when you're dealing with sources that are much smaller, you're not able to resolve the multiple images. And instead, what you see is that the source is magnified. So what you see is a light curve as you track the source, a light curve that looks like this. In the absence of second order effect, you see like the symmetric curve for an event with a single lens. And okay, and again, in this animation, so I just want to show the same thing happening on the upper panel. If you assume that the lens is in the middle, the yellow star, and we assume it's stationary, the ring is the Einstein ring of the star, and the source is the red circle. As it gets closer to the lens, the images are multiplied and stretched along the Einstein ring. We're not like resolving the images, but what we see is that as we observe the source, we see that the brightness of that increases, and it goes back to normal as the two objects move away. And that results in the peak that I showed you in the last slide. Now, if the lens happens to have a companion, for example, a planet, close to its Einstein ring, the companion, the planet in this case, will perturb the image it's closest to, and then what you would see in the light curve is a perturbation caused by the planet. And this is an example of what a planetary microlensing light curve would look like, but in reality, there are like so many different shapes depending on what your mass ratio is, what the separation is, what is the path of the source through the lens system. So I just want you to keep these two light curves in mind. We will talk about them more. And since we're like focused on the data-driven aspect of this whole science, it's really important to understand what sort of light curve shapes we're expecting to see. All right, so why Rubin? Just like everybody else is always emphasized on, we like Rubin because of its large field of view, because it goes much deeper into the sky, we can see much fainter stars, and because it has a long baseline. So all of these properties are good for us for the microlensing because it would allow us to find, basically to look for the microlensing events throughout the whole southern sky. And it helps us estimate the microlensing optical depth, which is basically the probability that a microlensing event would happen at a certain part of the sky. And Mark, who's going to talk after me, he will talk about that more. And we're looking for populations of stars, planets, and compact objects throughout the galaxy and the Magellanic Clouds. And it's also another point that is really important. We're talking about populations of stars, planet, and compact objects, but if we want to optimize a service strategy for finding these populations, we should know that these populations have different properties, so they would require a different set of conditions for observations. And then finally, we'll talk about Rubin in synergy with Raman, and I will talk about it in more detail in the next few slides. So since I want to talk about Raman-Rubin synergy, I want to briefly describe the Raman's microlensing survey to know how that's like basically applicable to what we're talking about. So as we all probably know, Raman is NASA's future space mission that is going to be launched late 2025. I think that's the last update. And the microlensing survey will take place during 6 seasons of 72 days throughout the whole survey time. And it's going to observe the galactic bulge with a cadence of 15 minutes. And it's estimated that it will look at 10 to the 8th stars and discover 54,000 microlensing events. And it's expected to find 1,400 planets and also a few hundred free-floating planets, planets that do not seem to be bound to any stars. So this is also something that we are so excited about. So, right. And when we talk about Raman and Rubin together, we're thinking of Rubin looking at the Raman's footprint, both at the same time as Raman and also at the times when Raman is not looking. So 2 different scenarios. And I will explain why these 2 scenarios are basically interesting for us. So the case where we want both of them to look at the same part of the sky simultaneously is because we want to measure the microlensing satellite parallax. And it's basically, it happens when 2 telescopes are looking at the same event from 2 different locations. And 2 different locations, and they're going to see the event slightly differently. So for example, in this case, if you assume that the lens star is the red star in here and the source star is this blue star moving through this path, Raman will see this event earlier because it's seeing that these 2 stars are aligned at this point. And then later, Rubin will see the event happening at this time since it sees the 2 stars are aligned at this point of time. Oh, sure. And okay. And so what happens is that, let me bring up the slide curve. What happens is that the 2 telescopes will see the light curves happening, the peak of the light curves happening at different times, and the maximum peak will be different from their point of view. It will allow us, measuring this parallax would allow us characterizing the events, and in particular, the synergies of Raman and Rubin is beneficial for measuring parallaxes of free-floating planets because of the distance between Rome and Rubin, which is 0.01 AU. So this is a very unique science case that will allow us characterize basically free floating planets that will be found by Roman. And we also talked about the two telescopes. So Rubin looking at the galactic bulge at the time when Roman is not looking. There are cases when, for example, we have wide orbit planets and you get the anomaly separately from the main event. And if the main event, for example, here happens to be at the time when Roman is not looking, we're going to miss the basically the most important part of that event, and we will just guess about what sort of event it was. But if Rubin will observe at that time and can get us that main event, that will be very much complementary to what Roman is finding. All right, so the microlensing subgroup has been very active ever since, trying to help optimize the service strategy, making sure it would be also beneficial for microlensing science. In 2018, we wrote 2 white papers. We suggested that the galactic plane, bulge, and Magellanic clouds will be covered within the white fast steep with a cadence of 2 to 3 days, and that the footprint be chosen according to the spatial density of the stars. You can imagine why, because microlensing is a rare event, and the more crowded fields you observe, the more likely you are to find a microlensing event. But at the same time, we are interested in looking at throughout the sky. So it's kind of like a trade-off between like how many events you want to find and where you want to find those events. And then we also suggested to have a deep drilling field on Roman's footprint to account for the sciences that I just described. And we have been developing metrics to help evaluate different OPSIM simulations and see which ones are more suitable for our science. The microlensing metric is like the main part of all those metrics that are now being run on the new OPSIM simulations. And there's been also work, extensive work on optimizing the galactic footprint, which is done by Rachel, and she will also give a talk today, and she will talk about that. And there's also Raman Rubin metrics that we have been developing, we are developing right now to make sure we can find the good solution for that. So in the next few slides, I will briefly talk about work done by my colleagues within the microlensing subgroup. The first part is the microlensing metric. And the microlensing metric is basically developed to help us basically evaluate the detection and characterization efficiency of the different OPSIM runs. The metric works in a way where like you have this input to the metric. So you have a set of simulated microlensing events that you use as an input to the metric. And these events are distributed across the sky according to the number density of the stars within the sky. And you can see a map of like one of the earlier distributions that was used. On the right-hand side, it's the metric runs on like the older versions of OPSIMs, 1.5, 1.6, 1.7, that I'm not like focusing on right now. But what I want to mention before I move on to the new updates is that the microlensing metric has 3 parts. The detection part ensures that there are at least 3 data points on the rising part with at least 3 sigma difference from the baseline in all bands. Second, there is a characterization component of that, which ensures that there are at least 10 data points within the Einstein time scale of the event. And lastly, there is another characterization component that ensures there is a fractional uncertainty of at least 0.1 on the Einstein time scale obtained from these events. And this last plot here, it shows the latest runs of this metric over the newest simulations. I want to particularly put this plot here to show how the new baseline is actually working for the microlensing science compared to the last, like the older versions. And on the y-axis, you see different components of the microlensing metric for different time scales. As I mentioned, different population of objects that we're looking at would require different conditions for observations. And for the stellar microlensing, we're basically focused on time scales between 30 days to 60, 70 days. Those are the most common time scales in the stellar microlensing light curves. There are also much longer time scale events that Mark will talk about. What I want to mention is that, so these two very red lines here, these are the results of the OPSIM on the older version of the OPSIM. And it shows that the new baseline 2.0 here is basically about like working about 50% better than the older versions of the OPSIM, which is really, really great. And then to maybe do some like guesses and estimations, in 2018, Sadiqa Sajjadian and Radek Polsky did the simulation on baseline 2018, and they found that with the strategy within the baseline 2018, where like the galactic plane was not included in the white fast deep survey, there will be about 14,000 events throughout the whole survey time. And assuming that the new baseline is like about 50% better than that, we are expecting at least like twice this number for the estimation of the new baseline, which actually can be more optimistic. So we're expecting to get more events, but we're just like we're sticking with this number for now. And I also want to mention some of the work that has been done by our colleagues in Argentina and Brazil. And Paul and Martin has been working on some aspects of the Rubin synergy. So the idea is that since Rubin will start observations a year, like sometime, not a little bit more than a year earlier than the Roman, the idea is that can we use that like precursor data from Rubin to identify more events from Roman and Rubin? And so they have been working on aspects of the synergy, and they are using like time steps from OPSIM to simulate LSSD light curves, and then they simulate Roman's light curve separately. They're using magnitudes from trilegal maps and using microlensing models from Pylema, putting them all together to simulate all these light curves. The idea is to put these light curves as input into classifiers that already exist to see if that helps basically identify more events. And then finally, I want to talk about the work that I am personally very interested in. So this is the light curve that I mentioned earlier, the plot that I mentioned earlier. So you can see a variety of shapes in these light curves. These are light curves of single lens and binary lens microlensing light curves. Depending on what the mass ratio is, what the separation is, you might get all these different shapes. And please note that these light curves are really like these are simulated for Raman. They're high cadence, so you can actually see a lot of detail. But with Rubin, a lot of these really small features will be missed. So the challenge is just like the challenge in many other fields is that there's going to be like huge volumes of data in the future, and analyzing each microlensing light curve with a binary lens is by itself a time-consuming process, and it involves humans looking at a light curves, and it requires computation power. And the idea was that when a human being just looks at these light curves here, it looks at the features, and with the background knowledge from microlensing, it can tell you some information about these light curves. It can tell you which of these light curves are more important, right? So the idea was that can we just automate that? Can we basically quantify all those little features that a human eye can get from these light curves and put it in an automatic system? And also, some of these light curves might need real-time analysis, real-time classification, because you want to schedule some follow-up information, follow-up observations. I did not mention the follow-up observations throughout my talk because Rachel will talk about that in more detail, but that will also like change a lot of things about a lot of the estimations that we're doing. So based on the idea that I described, the package that I developed was a set of functional fits to the light curves that was extracting all those information that the human eye is basically getting from the light curves, like looking at the deviations, number of deviations, where the deviations happening, what is the duration of the deviation, the symmetry of the light curve, how flat the top of the light curve is, and so many like others. And then here in this plot, I'm showing basically what I was doing was to, for example, quantify the symmetry and the light curves using some different methods and looking at the flatness of the top of the light curves, looking at how similar the light curves will be to free-floating planets, because like the light curves of free-floating planets will have a large finite source ratio, and therefore they will look like somehow like a trapezoidal function. And then trying to quantify the smooth large features that would be caused by the stellar binary lens events, and then eventually characterize the planetary signatures without actually feeding the models to the light curves. So getting all these different features, quantifying all these values, and developing more features, getting from like previous classifiers, what I was trying to do was to basically use these features to do different scenarios of classification, but done on the whole light curves with high cadence. That was what we were doing that time. So at this point of the project can be extended in two different ways. So for Rubin, the idea is to extend that data set that has been, the algorithms have been trained on, the features have been extracted from. The data set at that time did not include a lot of non-microlensing events that would be confused with the microlensing events, and also use like the newest methods that are developed, the newest classifiers that are now being run to classify these events. But on the Rubin aspect, I've been thinking of like totally like answering different questions. For example, with how efficient these features are for lower cadence light curves. And the most important question is that, can we say if this light curve is likely to have a planet if we don't see the anomaly? Or in some cases, there is no anomaly because just the mass ratio is too low or the separation is too large or too small. In those cases, can we still extract information from the light curve that can help us say how likely this light curve will have a planet? And I would love to, for that purpose, like to answer that question, I'm going to mention one of the algorithms that I've been working on, which is one of my favorites. It's the Chebyshev polynomial that I've been fitting to different types of light curves. And I've been fitting them with a Chebyshev polynomial of t's degree. And then I have tried to extract information by looking at the different coefficients, different combinations of the coefficients, and also like how well the polynomials are fitting different features within the light curve. And as another example here, I have a light curve of a binary lens microlensing event, which like a reasonably high cadence like here. And like you can see the fitted Chebyshev polynomials, and like I'm lowering the cadence. I'm looking at what's happening. I'm looking at what's happening when the actual differences are disappearing, and whether or not we can still extract that information from the light curve. Oh, sure, sorry. Whether or not we can still extract that information from the rest of the light curve. And also we should take into account something that has been basically like ignored all throughout these times, and it's not been included in the simulation. And that is the microlensing light curves will be affected by parallax. They will be affected by blending, and all these different factors can change like the subtle features in the light curves, and that can confuse us with the classification method. So here is what I'm right now working on to extend this to like lower cadence light curves to see how like how useful these information will be. So with this, I'm ending my talk. Thank you so much. I can take questions.
Great timing. Questions? Yes.
Great talk. This is related to just the slide that you just showed before. I know it's a work in progress, but do you have a sense of how many minimum number of detections you would need so that you do not lose that features? For example, in the first one, there are features, but as you lower the cadence more and more, those features are a little lost at the. So, have you optimized that yet, or is it a work in progress?
So do you like by number of detections, you mean like basically the data points,
Yes.
the list number of data points?
Yeah.
So it would really depend on like what you want to optimize this for. Like, for example, if you want to optimize it for like, I mean, you can't really optimize it for small planets because their signature is just too small for Rubin, and Roman is particularly planned to find them. But for larger planets and for like stellar binary events where the features are much larger, we can definitely do that. For stellar binary events where features are larger, we can, like, I mean, it's easier. I don't have like an actual number yet, but yeah, I think with the cadence of 2 to 3 days, as we suggested, that should be good for them. But with the planets, well, what I'm really focused on to find out if with that 2 to 3 days cadence, I can actually say how likely there is like a signature somewhere, even if we have missed a signature. So that's like the goal. Yeah, the ultimate goal.
Thank you. Yeah.
I think in the middle of your talk, you mentioned 14,000 detections are predicted. Maybe I missed it, but could you remind what models were assumed, or is that extrapolation of existing observations?
Sure. So the way that simulation was done was that they had used the Byzantine galactic model to basically simulate a set of microlensing events. And and they by assuming different opsim simulations and some detection criteria, they decide like which of these events will be detected. And then they evaluate the detection efficiency for various like service strategies. And the one that I mentioned, the 14,000, was the one that was more similar to the retro baseline that is now like the representative of the older baselines. Did I answer your question?
Excellent talk, thanks. I was wondering if the features that you're using are overlapping with the features that DM from LSST are already going to calculate for the light curves.
Well, some of them, yes.
Okay.
So for example, one of the trivial things that you can do with microlensing events is to fit them with a single lens model, which is not like something hard to do. I mean, it's like fairly simple process, and it gives you really good information about how similar the light curves are to a single lens model, and like any deviations could be signs of something going on. But the other thing to consider with that is that if you want to do it like many times, like with different sections of the light curves, it's not necessarily that efficient, especially if you're working with sections of the light curve where like the peak is missing, or like some important part of the light curve is missing. But yeah, so some are, but most of them are not.
Great talk. I was wondering, you mentioned like 3 protein planets as some very exotic, exciting. Are there some other more speculative things that one may discover with the Rubin combined rare events?
So yeah, I mean, most of the discoveries that we anticipate are exciting for us. The free floating are particularly exciting for most people, not just like microlensers. But yeah, like finding more lensing events in the Magellanic Clouds would be also something exciting that we would love to investigate.
Thank you.
And while the next speaker sets up, I'm going to take prerogative and ask the last question.
Sure.
So there is the deep drilling fields are not going to help you, right? Because they are not on the galactic plane. There is a pencil beam proposal for sort of microsurvey or anyhow a concentration of higher density observations in one particular field in the galactic plane. How much does that help you anchoring your efficiency for these kind of metrics on the regular observations if that happens?
Well, I haven't exactly investigated that, but like in the newest Opsim runs, it generally like it doesn't seem to significantly change the results. But I personally have not investigated specifically for the metrics that I'm developing.
Thank you. And let's thank Somayeh again for setting the stage for today.